Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to talk about robot inverse kinematics. Robot inverse kinematic is one of the very important practical aspect in robotics, in the sense that here we are talking in terms of the workspace. Okay, and for our robot to move in the workspace, what should be the joint angles if I am talking about say a manipulator. So, that evaluation is actually what we call about the inverse kinematics. Okay. So, I hope that by the end of this lecture you will be able to understand what are the challenges in evaluating the inverse kinematic solution and what are the ways by which we can get the inverse kinematic solution for a planar manipulator, and I have also covered a wheel robot here in today's lecture. So, the content which we are going to see are, say, I will be introducing the topic to you, then we will be seeing the what are the various issues, then we will be looking at the algebraic solution for the inverse kinematic, and then geometric solution, and finally the inverse kinematic solution for the differential drive robot. Okay. So, in inverse manipulator kinematics, basically suppose you are given a scenario here, okay, and in this scenario say you have a table on which an object is placed, okay. We attach a frame to the object, we call that as the goal frame, and a corner of the table is called, a frame is attached over there, that we call as the station frame. I have a robot here, and at the base of the robot we have a base frame over here, and then I can define a wrist frame which is attached to the wrist and a tool frame attached to the tool. Okay. We may have a camera which is looking at the entire environment. Okay. So, here inverse manipulator kinematics, actually what we are trying to do is that we are essentially will be finding out the joint rotation. Okay. So, here in inverse kinematic, for the given desired position and orientation of the tool frame, okay, relative to say the station frame, okay, the question is how do we compute the set of joint angle which achieve the desired result. Okay. So, I am given the tool frame description with respect to the station frame, and my job is to find out what are the joint angle. So, this problem is actually split up into two parts. First part is we find out the description of wrist with respect to the base frame, and then we use the inverse kinematic to solve for the joint angle. So, in solvability, what we are trying to do is that we are given the description of nth frame with respect to say the 0th frame, and we calculate the various joint angle. Okay. If I am talking about say a 6 degree of freedom manipulator, then naturally I am say I have the description of frame number 6 with respect to 0th frame, and of course this can be, this we get by various transformation multiplication, that is multiplication of 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1 and 1 to 0. Now, this expression looks like something this. Okay. So, it is a basically 4 by 4 matrix, okay, which has got say 16 values. Okay, and this R which you are seeing over here is basically the 3 by 3 matrix, orientation matrix, okay, which we also call as the rotation matrix. Okay. So, this transformation matrix, the last column actually that describes the position, okay, of the say frame number 6 with respect to 0th frame, and this R describes the orientation. Okay. Now, finding out of the inverse kinematic problem. Okay. So, basically say for a 6 degree of freedom manipulator we have the 6 unknowns, that is the 6 joint angle. Okay, theta 1 to theta 6 we need to find out, and to get that what we have out of these 16 values, as we see the 4 values are of no use. Okay. So, 4 values are trivial, these 3 values are for the position, and out of this R we know it is a 3 by 3 matrix. So, we have the 9 values over here. So, out of these 9 only 3 independent. Okay. So, essentially what we have is 3 plus 3. So, 6 equations with 6 unknown. So, this way we can solve for all the 6 joint angle. Okay. These equations are non-linear and transcendental and difficult to solve. Okay. For say Puma 560 robot, many of the link parameters are 0. Okay. But in a general case of 6 degree of freedom manipulator, solving these equations are really difficult. So, what are the challenges faced in finding inverse kinematic solution? So, the first challenge is existence of a solution. Many a case the solution itself may not exist. If your object is the outside of the workspace, okay, it will be difficult to get that object, okay, using the end effector. So, in that case you are not going to have any solution. Then we may have the problem of the multiple solution. Okay. So, to reach say one position of the end effector, one position and orientation of end effector, there can be more than one ways. So, the question arises which way we should select. Okay. So, that is also going to be a challenge, and then how do we get the solution? That is also a challenge. Okay. What method we are going to adopt for getting of these solutions, as these equations are going to be the nonlinear equations. Okay. So, we will look at these challenges one by one. Let us look at the first challenge, okay, that is the existence of a solution. So, before I define this challenge, okay, discuss this challenge, let us define what the workspace is mean by. Okay. So, workspace is volume of space, okay, which the end effector of the manipulator can reach. Now, for a solution to exist, the specified goal point must lie within that workspace. As I said, then only we are going to have a solution. Okay. So, there are two types of workspace which are there. One is what we call as the dexterous workspace. It is that volume of space which the robot end effector can reach with all orientation. Okay. And the reachable workspace is the another classification of workspace which says that it is the volume of space which the robot can reach in at least one orientation. Okay. So, if I take the example of a 2-link manipulator as it is shown over here. Now, if say both the lengths are equal, L1 is equal to L2, the reachable workspace is going to be a disk of radius say 2 L1, alright, and the dexterous workspace is going to be a simple point, the origin, alright. So, in this first case your reachable workspace is going to be say this one, the disk of radius 2 L1, and the dexterous workspace is going to be just say this is your one link and this is your another link. So, your dexterous workspace is going to be just this point. Okay. And if L1 is not equal to L2, then there is no dexterous workspace. Okay. And the reachable workspace is just going to be the disk ring of outer radius say L1 plus L2 and the inner radius of L1 minus L2. So, it is going to be something like this, say this is your L1 and this is your L2. So, you are going to have this is going to be the disk outer radius, and when your L2 is in this configuration, okay, so your end effector is over here, this is going to be the inner radius. Alright, let us look at the next challenge, and that is the multiple solution. So, suppose you have a robot over here like this, okay, and end effector is at point A, alright. Now, this if the robot has to reach say this point B, it can reach either using this way, alright, or it can reach using this way. So, you have the two ways of doing it, alright, two ways of reaching to the same point. Now, the question is which way we should adopt, alright. So, there is a general criteria, and that criteria says that the solution in which the minimum number of joint motion is involved, we should go for that solution, okay, unless some issues are there such as say an obstacle is over here. Now, in this case, if your obstacle is here, naturally you cannot go by this solution. So, naturally you have to adopt this solution. So, this is how it is done, and for say Puma 560 there can be 8 solutions for a single goal. Okay. And in general, the more the non-zero link parameter there are, the more ways there will be to reach the certain goal in the workspace. Alright. So, here is some of the data for a manipulator with say 6 rotational joints. If 3 link lengths are 0, then you are going to have number of solution less than 4 or equal to 4. If only 2 link lengths are 0, then the number of solutions are going to be less than or equal to 8, and if only 1 link length is 0, then number of solutions are going to be less than or equal to 16, and if all link lengths are not equal to 0, then again your number of solutions are going to be less than or equal to 16. Okay. So, a general criteria is that, or the general conclusion is that, the more the number of non-zero links, the more the number of solutions. So, before we proceed further, let us look at some useful definition. What do we mean by a function being linear? Okay. So, a function f is linear if it satisfies 2 axioms. These are additivity and the homogeneity. Okay. So, additivity means that if the value of function for say x plus y is equal to same as the value of function for say input x and value of function for input y. Homogeneity says that if you multiply this input by say a constant alpha, then the value of function alpha x is going to be same as alpha into x, okay, for a scalar value of alpha. So, this superposition principle allows us to a complex problem to be broken into simpler linear parts which are very common in robotics and AI signal processing. Okay. We say a manipulator is solvable if it has a unique solution. A term is used what we call at closed form, and this means basically a solution can be computed algebraically and it provides all the solution. And the numerical method is basically, as all of us know, it is a iterative process, and the algebraic one method uses algebraic identities to substitute and to solve. The geometric method similarly utilizes geometric relationship such as say law of cosine etc. And subspace is a smaller region. For example, a circle in a plane sphere is in xyz space. Okay. Next challenge, the third one, is the method of solution. Okay. You see, these manipulator equations are nonlinear. So, we do not have a general method to solve these equations. All systems with revolute and prismatic joint having a total of 6 degree of freedom in a single series chain solvable. Okay. However, the general solution is going to be the numerical one. Okay. And robots with analytical solution have several intersecting joint axes. Maybe we will be discussing this a little later further. Manipulator, as I said, is solvable if joint variables can be found by any algorithm, and the algorithm should find all possible joint variables associated with the given position and orientation of the end effector. The main methods are, as I said, the numerical one and the closed form. Numerical one are iterative in nature, and closed form could be algebraic as well as geometric. We are going to see both algebraic and geometric here in today's lecture. Okay. So, always we prefer an analytical solution, okay, over a numerical one, as numerical solutions are time consuming because they are iterative. Okay. You need to perform a sufficient number of iteration in order to closer to the solution. Okay. So, there is a sufficient condition that a manipulator with 6 revolute joints will have a closed form solution, and that condition is that the 3 neighboring joint axes intersect at a point. Okay. Now, let us look at the kinematics. Kinematics can play a large role in both the computational requirement for the robot and its range of motion. Okay. Most industrial robots have simple kinematic to reduce the computational burden, because we want to go for the online control also, right. So, we do not want that the computation itself takes lot of time. Okay. So, often these have spherical wrist, okay, and as I said, if the three axes are intersecting, okay, so we are going to have the closed form solution as we have seen. Okay, the three neighboring joint axes intersect. Okay. So, this condition could be something like this, say the wrist joint, wrist rotation, that is joint 4, wrist bending, that is joint 5, and flange rotation, that is joint 6, all intersecting at a point. So, most industrial robots have these spherical wrist because their three axes are intersecting, and a spherical wrist is a three joint robotic end effector design, basically where the three joint intersect at a single common point, creating a spherical motion envelope, and almost always have three joint axes. For almost all the industrial manipulator have the three intersecting joint axes. It is the Piper solution which guarantees the closed form inverse kinematic solution. Okay. And see, there are, when we are going for these solutions, we will be getting multiple number of sine and cosine terms, and evaluating these sine and cosine terms is always a challenge. Okay. So, usually there is a lookup table, we can store both the sine and cosine values in a lookup table, and need only 1/4 of the full table in order to have all the lookup values. Now, let us look at the inverse kinematic solution. So, first I am going to take this algebraic solution for this 3 degree of freedom planar manipulator, and then I am going to take the geometric solution of this 3 degree of freedom planar manipulator, and finally I am going to take inverse kinematic solution for a wheel robot. Okay. So, this example we have already seen earlier. Okay. It is a 3-link manipulator, 3 joint manipulator, and in this 3-link manipulator we can start with assigning the frames. So, this x0 y0 is the inertial frame or base frame. Then I have x1 cap y1 cap which is attached to the first link, x2 cap y2 cap is attached to the second link, and x3 cap y3 cap is attached to the third link. So, the angle between, say, the base frame and the x1 cap, that is the first link, is this theta 1. Okay. And similarly, the angle between the first link and the second link, this is theta 2, and similarly the angle between the second link and the third link, that is theta 3. So, for, and say link lengths are L1 and L2. I have not mentioned here L3 because we do not require that here, and for here I am following the notation as given in the robotics textbook by J.J. Craig. Okay. So, as per that notation I am following the frame assignment. So, this is the DS table. Okay. We have already seen how this DS table is obtained earlier. So, I can write the description of frame with respect to frame 0, which is essentially the description of the wrist frame with respect to the base frame, and this is going to be the my matrix. Okay. So, this is my rotation matrix R, and this is the position vector for the third frame origin position with respect to the 0th frame. Alright. So, this is what I get by simple multiplication of the transformations for, that is 3 3 2 2 1 and T 1 0. And I can get these transformations using the transformation matrix T n 0. This expression we have already seen, and we can put up these values from this DS table. Alright. Further, this is a very simple case, right, a very simple case of the planar manipulator. So, we can get these values geometrically also. Okay. For example, this end effector position with respect to the x axis is naturally going to be theta 1 plus theta 2 plus theta 3, and that is what this rotation matrix tells us, and these positions are going to be what, L1 cos theta 1 which is this length, then L2 cos theta 1 plus theta 2 which is this length. Okay. So, this length is this one. Similarly, this length is L2 sin theta 1 plus theta 2, Okay. So, this is this term, and this term is actually your L1 sin theta 1, which is this term. Okay. So, this way we can get that using trigonometrically also, and using transformation matrix also. All right. Now, suppose I am given that where my end effector is. Okay. So, I am given the say the position of end effector as x, y, and I am given the orientation of the end effector as say angle phi. So, now the question is, how do we calculate what joint angles are needed, okay, for the manipulator to get this x, y position and the phi orientation. Okay. So, my task is essentially to determine these three joint angle values. All right. So, we can compare these two equations. So, from here basically you see cos phi is going to be cos 1, 2, 3, which essentially means cos theta 1 plus theta, this essentially means cos theta 1 plus theta 2 plus theta 3. Likewise, other terms are defined. Okay. So, I can compare this, and my x is going to be this one, L1 C1 plus L2 C1 2. So, this term is going to be this one, and this term is going to be this one, and of course, phi is going to be theta 1 plus theta 2 plus theta 3. So, now the question is to evaluate these joint angles. Okay. So, we can do some mathematical manipulation with these equations. Okay. So, say I take the square of both those previous equations, x square plus y square. So, this corresponds to the first equation expansion, and this corresponds to the second equation expansion. Then I can take L1 square term over here. So, and I can couple this term say with this term. So, I get this term. Then similarly I can couple this term. Okay. So, I get this term, and similarly I can write this term by taking 2 L1 L2 common from over here. Okay. So, this one, this is what I get, L1 square plus L2 square, and this is 2 L1 L2, and this is cos theta 1 minus theta 1 minus theta 2. So, essentially you will be getting cos theta 2. Okay. So, this way I get cos theta 2 value. Here I know this x1 x square, I know y square, because I am given the end effector position. L1 are the link lengths, and so L1 L2 are the link length here. So, I know. So, this way I can find out the value of C2, I can get the value of S2, and then I can get the value of theta 2 like this. Okay. So, basically I am taking the inverse of tan over here. Okay. Here we are using r tan 2 function, basically which takes care of the sign in the third quadrant. Okay. Because in the third quadrant your x and y both are going to be negatives. All right. Now we have evaluated theta 2. Now my task is to get the value of theta 1 and theta 3. Okay. So, to get the value of theta 1, again we go back to this equation, L1 C1 plus L2 C1 2. Okay. So, let us expand this part over here. So, I get it like this. Okay. And now what I do, I combine these two part. Okay. So, I take C1 out, and so I combine this part here. Similarly, I write here L2 S2 like this, and this one, and say this I represent by K1. So, I have K1 C1, and say I represent this by K2. So, I have K2 S1. Similarly, I can write for Y. So, I get K1 S1 plus K2 C1. Okay. Now, let me define this K1 and K2 through a triangle, and say this is R. So, this R will be square root of K1 square plus K2 square, and say this angle gamma is going to be A tan 2 K2 by K1. Okay. So, from here what I get, basically K1 is going to be R cos gamma, and K2 is going to be R sin gamma. All right. So, now what I do, I am doing this manipulation, as I said, in order to find out the values of theta 1. Okay. So, now I can substitute this K1 as R cos gamma here, and K2 as R sin gamma. So, this is my equation. I can get x by R from here, y by R from here. Okay. And this is nothing but cos gamma plus theta 1, and this is sin gamma plus theta 1. Okay. So, I can get gamma plus theta 1 as this one, y by R comma x by R, okay, or y x. All right. So, here from here I can get value of theta 1. Okay, so this way. Now you see y and x I know because I am given the end effector position. Do I know k2 and k1? Yes, I know k2 and k1 also because I have already evaluated theta 2, right. So, I know L2 sin theta 2 and similarly I know L1 plus L2 sin theta 2. So, I know k2 and k1 also. So, this way I get the value of theta 1, and if x and y is equal to 0 in the previous equation, okay, the previous equation becomes undefined, okay, and in that case we can take theta as arbitrarily, and to get the third value, that is theta 3, we can just equate any one of these, okay. So, my theta 1 plus theta 2 plus theta 3 is going to be equal to 5. I have already evaluated theta 1 and theta 2. So, this way I will get the value of theta 3. So, in this inverse kinematic solution, what we have done, we were given the value of x y, that is the position of end effector, and we have been given the orientation of the end effector, right. And what we did, we evaluated the three joint angles, that is theta 1, theta 2 and theta 3. Okay. Next, let us look at the geometric solution. Okay. So, geometric solution is much simpler. So, suppose this is your manipulator over here, okay, this is your manipulator, and in this case we know that we are going to have the two solutions, right, it is a 2 degree of freedom manipulator. So, this is one position and this is going to be the another position, right. So, for this position you have this joint angle. So, this is theta 1 and this joint angle is say theta 2, okay, and say these other angles are defined, say this angle is beta which joins the end effector position with the origin, okay, and say this angle is phi. Alright. So, what I am given? I am given this position of the end effector x y I am given. My job is to find out the theta 1 and theta 2. Alright. So, what I can do is that if this point is x y, so in this triangle naturally this length is going to be under root x square plus y square. So, I can apply the cosine law in this triangle. Okay. So, what is this angle going to be? So, this angle is going to be 180 plus theta 2. It is basically 180 total minus and minus theta 2. So, it is 180 plus theta 2 basically. So, I can apply the cosine law, okay, and from here I can get the value of cos theta 2 over here. Okay. Now, you see, in order this triangle to exist, the naturally the distance of the goal point, which is this one, that must be less than or equal to the sum of the link length. Okay. That is your goal point has to lie in the workspace of the manipulator, and this condition could be checked at this point in a computational algorithm to verify the existence of the solution. Okay. And this equation is solved for value of theta 2 that lies between 0 to minus 180 degree, because only for these values your triangle is going to exist. Now, as I said, in this case we are going to have the two solutions. So, what the other possible solution is? Okay. So, the other possible solution will be corresponding to this one basically. Okay. So, this is theta 2 dash, alright. So, that is your theta 2 dash is going to be minus theta 2, alright. Okay. And once I have got the value of theta 2, I can try to find out the value of theta 1. Okay. So, how can I do that? Let us see here what is this angle beta. I know x and y. So, I can get a beta as r tan 2 yx, and what will be this angle psi? This psi I can get as basically, again I am applying the cosine law. Okay. So, it is under this under root x square plus y square whole square. So, it is this length, alright, and plus L1 square minus L2 square divided by this 2 L1. Remember, this is your L1 and this is your L2. Okay. Alright. So, this way I can get this value of cos psi, and then you see what is my theta 1? This theta 1 is basically your beta plus psi. Okay. So, it is this value plus this value, because this value and this value they are going to be the same. Okay. So, theta 1 is beta plus psi. So, the arc sine must be solved for psi between 0 and 180 degree. okay, and where the plus sign is used if your theta 2 is less than 0, okay. So, theta 2 is less than 0, that is your theta 2 is negative, and you use the minus sign if your theta 2 is greater than 0, alright. So, this way we can get, and then if you know theta 1 and theta 2, I can get the value of theta 3 because I am given the final orientation. Okay. Next, let us look at the differential drive robot kinematics. Okay. Here again I am interested in finding out the inverse kinematic solution, and that inverse kinematic solution what I am looking at is that I am given my robot velocity, okay, and I am interested in finding out what are my wheel velocities. Okay. So, here the two independently driven wheel placed either side of the body, alright. Left wheel linear velocity, these things we have already seen in our last lecture in the forward kinematics one. So, right wheel linear velocity is RUR, where this UL and UR are nothing but the angular velocity. So, these are the tangential velocity basically, which we say that V is equal to R omega. So, these are those terms. I can write the kinematic equation here. Okay. Again, I have explained how this kinematic equation we get in the previous lecture. So, here what I have all, I have got the velocity of the robot in x direction and y direction, and the spinning of the robot, that is the angular velocity of the robot, and here we have the left wheel angular velocity and the right wheel angular velocity. So, this term I can say as a what we call a Jacobian, and this term I can define as P dot. Okay. So, in the forward kinematics what we had basically, we were given wheel velocities and we calculated the robot velocities, and in the inverse kinematics I am given the robot velocities and my job is to calculate the wheel velocities. Okay. So, I can take this P in P dot by taking the inverse of Jacobian and then multiplying by Q dot. Okay. So, this is how I can get that. Now, the question is, this our matrix is a non-square matrix, this is a non-square matrix, then how do we get the inverse for that? Okay. So, that is the challenge. So, computation of non-square matrix inverse under the condition that J is a full rank, okay, and this rank is defined, of course, the minimum value of the number of rows and the number of columns. So, case 1 could be if number of rows are more than number of columns, then Q dot is over specified, and this is how we can define the Jacobian, and if your number of rows are less than number of column, then the Q dot is under specified, and this is how we can calculate the Jacobian. Okay. So, in the differential drive case, our is basically 3 row 2 column matrix. Okay. So, we can define this Jacobian by the first way, right. So, this could be, I can write this right here. So, this way I can define that and then I can evaluate that. There is a practical approach for finding the angular velocity of the wheels, and that we could do this way. For example, the linear velocity of the robot center, that is going to be say left wheel linear velocity plus right wheel linear velocity divided by 2. I can write it in terms of the angular velocities of those wheels, and so I get this equation. Okay. Similarly, I can define the angular velocity as the difference of the linear velocities, two linear velocities of the wheel divided by the distance between the wheel, okay, which is 2d. Okay. And again I can substitute this one, and so I get this equation. So, we have basically the two equations with say 2 unknown over here, and this way I can solve for UR and UL. So, this is the practical approach for finding the angular velocity or the inverse kinematic solution for this differential drive robot. This animation shows essentially the inverse kinematic solution for this wheeled robot. Okay, and here you see that we are given the linear and angular velocity of the robot, okay. And for given linear and angular velocity of the robot, we are getting the two wheel velocities, that is the left wheel velocity and the right velocity is here, okay. And here are the fixed parameter, that is the wheel radius and the distance between the wheel. So, here we can see by varying these parameters, okay, as well as by varying say these velocities, our inverse kinematic solution changes, okay. So, let us summarize what we studied today. So, inverse kinematic is the inverse problem, finding joint configuration that achieves desired end effector pose. We could have the closed form which is fast, but it is limited to a specific type of robot geometries. Then we have the numerical inverse kinematic, which Jacobian based method work generally, but need handling of the singularities, and that I am going to discuss in our next lecture. What are the singularities, how to avoid and all those things. And for the wheel robot inverse kinematic, that is the one which I have dealt here, that is the differential drive robot. What essentially we do is we find out the individual wheel angular velocities given the motion, that is the translational velocity as well as the angular velocity of the robot, okay. So, these are the references which you can look at it, and thank you very much.